Alpha, beta, and gamma radiation all come from the nucleus of atoms. They have different masses and therefore different energies, but they are all invisible to the human eye. So how can we tell the difference between them? The answer is simple. There are two tests we can do to determine the type of nuclear radiation we are studying. Firstly, the different types of radiation travel different distances in air. This is to do with the size of the particles and the charge on them. Alpha particles are made of 2 protons and 2 neutrons, so are as big as a small nucleus. Alpha particles have a relative charge of +2. This means that they will strongly attract negative charges, such as electrons, and strongly repel positive charges, such as other nuclei. The air is made up of lots of different atoms in a mix. It is about 80% nitrogen gas, 20% oxygen gas, and other gases in trace amounts. I am being very approximate. The nitrogen nucleus has 7 protons in it, and so a relative charge of +7. Oxygen has 8 protons, and a charge of +8. A particle with a charge of +2 is going to interact with all these other charges surrounding it to slow it down a lot. Its size also means that it's more likely to hit other atoms and slow down. In air, alpha particles only travel a few centimeters. If you put something more dense than air in between the detector and the alpha source, it is very unlikely that any alpha particles will reach the detector. Although a sheet of writing paper is flimsy to the average human being, it is more than dense enough to completely block an alpha particle. So, to test for alpha particles, we need to set up a source and a detector and put them in line with each other. If the detector can only pick up radiation from our source a few centimeters away from it, it is alpha decay. If we set up our detector so it is picking up radiation, we can do the second test for alpha radiation. If you place a sheet of paper between source and detector, and the detector stops picking up radiation, then this source is definitely an alpha source. Beta radiation is either an electron or a positron. The mass of these particles is much, much smaller than the average alpha particle. That means that it is much less likely to hit another atom or nucleus and slow down or stop. The beta particle only has a charge of relative magnitude 1. It is either -1 for a beta negative, an electron, or +1 for beta positive, a positron. This means that the beta particle will be less influenced than an alpha particle. In air, a beta particle can travel up to about half a meter. Because it is so much smaller, it will more than likely pass through a sheet of paper. To test for beta decay, you need a more dense material. Most metal will do the job, but typically we say that beta decay is stopped by a sheet of aluminium. To test for beta, our particle has to have first failed the alpha particle test and travelled more than a few centimeters in air and also passed through a sheet of paper. If a sheet of aluminium stops the radiation being picked up, and the radiation only travels a few tens of centimeters in air, then it is beta radiation. You can use the absorption effects of beta radiation to set up an electronic thickness detector for paper production. If the level of beta detection falls below a certain level, you know that paper has become too thick, and you can adjust your system so that it becomes thin again. Gamma radiation is the smallest of all. It isn't a traditional particle, but can be described as a traditional wave. This means that it doesn't have a mass or size, so shouldn't interact very much with the surrounding matter. If you set up our detector/source system carefully so that they are perfectly lined up, you should be able to detect gamma radiation over any distance. If the source fails the alpha and beta distance in air test, then it is almost certainly gamma radiation. Gamma will definitely pass through paper, and it will pass through thin to medium thicknesses of aluminium. To have any effect on our radiation, we need a very dense material. This material is usually lead. If you place a sheet of lead in between the detector and source, it should significantly reduce the amount of radiation detected. A gamma source can be introduced to fluid systems to detect defects in them. Water pipes underground can have a radioactive dye added to them, so that a concentration of gamma radiation on the surface of the street would indicate a rupture in the pipe underground. Human pipe systems, such as circulation systems inside the body, can be monitored in the same way. By injecting a radioactive dye into the veins, you can detect the flow of blood through the system using a gamma camera.